Okay, welcome everyone. Today we have the pleasure to continue with the course of density functional theory presented by Dr. Paul Ayers. So welcome, Dr. Paul, and go ahead with the course.
Okay, thank you. Okay, so I teased this at the end with the Lagrangian because we were talking about the one electron reduced density matrix functionals, right? So we're going to go back to that, and we'll work through it with some level of detail, and then we'll try to see what we can learn about one electron reduced density matrix functional theory. Okay. So let's remember the context. We have the electron-electron repulsion functional, and it's a minimization of the electron-electron repulsion of the in-electron density matrix, right? Subject to some constraints, and the main constraint is that the partial trace, so if you get rid of all but one of the electrons of the in-electron density matrix, then you get the one electron density matrix. And it doesn't matter which electron you decide you want to leave out. Right? You can trace over all but one of them. It doesn't matter. You always get the same one electron density matrix. And we said this is quantum optimal transport. In fact, quantum optimal transport would include the fact that these are different density matrices. Okay. That's not really so interesting directly, but maybe just to tease something that may be interesting to some of you. If we did this of I'll call it something different. I'll call it the gamma 1, gamma 2, we did minimize trace of some, can be anything basically. We'll call it a cost function, gamma. And then we did gamma trace to gamma 1 trace gamma 2. This ends up being something they use in computing. So here is one quantum state, and out comes an output quantum state. So you have an input and an output, and some costs of taking the input to the output. And so if you want to find the optimal channel, you have to minimize over the cost of all the density matrices consistent with this input and this output, right? So this ends up showing quantum computation as something. So of course, very similar to this problem, the only thing here is that we want to deal with more than 2 electrons. And we have all of them are the same because it doesn't matter which one we leave out, right? Just as a side note, it wouldn't cost anything extra if you said, oh, I want to have the first of these tracing out to an alpha spin density matrix and the next to a beta spin density matrix. If you wanted to spin resolve it, it would be no problem. Right? It just makes my notation harder, and the notation is hard enough as it is, right? Okay, now there's some other things that I have to constrain. One is that the density matrix has to be non-negative, right? And it has to have the right trace, right? So. Okay. So these are other constraints that I have to somehow impose on this problem, okay? Now, I told you last time, I'm going to erase my digression. So I told you this isn't a very nice function. We've already done some work on this functional. We know, for instance, it's not going to be differentiable. It will be continuous. It's unpleasant, right? So we're going to regularize it, and we use standard trick. We add, this is the energy, we turn it into a free energy, right? So we regularize it, and we add tau trace of gamma times. Okay. This is fine. Now, why did I choose this one? I could have chosen anything I wanted to regularize this, right? But this is beautiful because one of my constraints was that this is positive semi-definite, right? And log of gamma, right, is only defined when gamma is positive semi-definite. In fact, only when it's positive definite, in fact, right? Otherwise, this thing blows up. So adding this penalty automatically means that once this term starts to get close to being non-positive definite, this penalty explodes, right? And I don't need to worry about it anymore, right? So that wins me something. I get to take that away, right? This is standard trick that people do in density matrix theory. They do this log penalty to try to keep you away from the boundary, right? Okay. So now I'm in position and I can write down my Lagrangian. My Lagrangian is my objective function. Then I have Lagrange multipliers for these constraints. Now they're all kind of the same constraint, right? So I'm going to be really sloppy with it. I'm going to write it down for just one of them and know that I have n copies of this constraint, right? So my constraint is that the trace of gamma minus gamma, this matrix is supposed to be 0, right? So I just pulled this over to the other side. I said, well, this matrix is supposed to be 0. Then I need to add a Lagrange multiplier. So that's my Lagrange multiplier constraint for this. And actually, it doesn't really matter, but for reasons that will be obvious later, I'm going to use my Lagrange multiplier with a plus sign there instead of a minus. So it just changes the sign of the Lagrange multiplier, but my equations are going to look nicer if I do it this way. And then I have this constraint. Now, technically, I don't need this constraint, right? Because if the partial trace of this is equal to the density matrix, and the total trace of it is also going to be fine, right? So it can't be wrong because, but I'm going to add it in. So I'm going to add on a constraint, lambda, that's trace of gamma. Okay. So that's my Lagrangian. Just normal throwing Lagrange multipliers in front of all my constraints. Nothing fancy here, right? Now I have to take the derivative of the Lagrangian with respect to the density matrix. That has to be 0, right? That's the next step, always, right? So what is this going to be? Well, this is a linear function, so it just gives me VE. This is also linear. This is a trace over everything with H on gamma. So this is plus H. This is also linear. It just ends up giving me plus lambda. Right? And then the final thing that I have to deal with here is this constraint. So start by saying the derivative with respect to the gamma is log gamma minus I. So we'll write it out, tau of log gamma minus I. And then I have to take the derivative with respect to log gamma. And that's going to be gamma over gamma. This is just I. So this term and this term cancel out. So that's why we did this minus I. It's just to make our math ever so slightly easier. Okay. So this is my constraint. Okay. And I can, in fact, we can just write this as log gamma is H plus BE plus lambda over tau with a minus sign. Okay. So this is a key equation. Now I'm going to want to get rid of my gammas, right? So the first thing I'm going to do is I'm going to get rid of my gammas. I'm going to have an expression for log gamma. I'm allowed to put it in, right? So I'm going to put my expression for log gamma into this formula. And I'm going to get a new expression for my Lagrangian. Now, trace of BE gamma plus tau trace of gamma times minus H plus BE plus lambda over tau. Trace of okay. Now, if we observe here, this tau and this tau will cancel each other out. I have a minus H gamma and I have a plus H gamma. So this term goes away. I have a minus lambda gamma and a plus lambda gamma. So this term goes away. I have a VE minus times gamma and a VE plus times gamma. So this term goes away. And then all of this stuff goes away. Okay. So I end up with equals tau trace of gamma, the minus sign, minus trace of H gamma minus lambda. Okay. So I just canceled out all this stuff that I'd like to cancel out. Okay. Now, this still doesn't get me all the way to where I want to go, because I still have this gamma in here, and this isn't super nice. Okay, so we're going to okay. So I need to think about how I'm going to deal with this expression. And what I'm going to do is I'm going to use this expression and say, oh, also gamma is e to the minus H plus BE plus lambda over tau, right? And this should probably look familiar. This is one electron integral plus two electron integral, so that's just the Hamiltonian, right? So this is just e to the -1 over tau times some Hamiltonian. I'm going to call this the effective Hamiltonian plus lambda. Okay, so that's the formula I have for gamma. Okay. So now my Lagrangian is equal to minus tau trace e -1 over tau e, oops, times h effective plus lambda minus trace of h gamma. Okay. Now, this is really the standard trick that we play when we're doing when we're doing density matrix type stuff. And the thing that we're going to want to do now is we're going to want to, the supremum of this Lagrangian, which depends on h, is going to be equal to our electron, right? So this is the nature of, we just wrote the dual functional. So we went from the primal problem, now we've written the dual problem. And I mean, I did not prove that there was no duality gap, but then the maximum of the dual problem is the same as the minimum of the primal problem. So this is the standard sort of trick. Okay. Now, this is still a little bit unpleasant, because the lambda here is showing up, right? And I'd like to get rid of the multiplier also. Okay, so I'm going to get rid of the Lagrange multiplier now. That's my sort of my last step in this procedure, is to get rid of the Lagrange. Okay. Well, there's something fortunate that I know from, again, this expression, which is I know that trace of gamma equals 1. That's my constraint, right? So let's just think about, what does this mean? Here now. We'll wait and see if it changes its mind. I think I have once again overwhelmed the board. Okay. Okay, now let's see how smart I am now. This is the question. The Lagrangian expression I had was equal to minus tau e minus 1 over tau. This, remember, this is temperature, so this is inverse temperature, so this should feel good. Some h effective, remember, and I'll write it second. Plus lambda. And I left off trace. Something's fishy here. Unfortunately, something's fishy here, and I am not sure why it's fishy, but we're going to see what I can figure out, and then we'll, in the end, I may have to give you an answer without actually telling you where I made the mistake, because it's somewhere that embedded deep inside something, right? I'm recognizing something fishy. So this I am. Okay. Okay. Anyway, I know the shape of this result, so we'll just see what we get out of this at the end. Now I wanted to use the fact that the trace of e minus 1 over tau of h effective plus lambda equals 1. And that's enough to tell me that trace of e to minus 1 over tau h effective times e minus lambda over tau equals 1. Okay, yeah. Okay, so normally you can't take an exponential of a sum and turn it into a sum of its exponentials, not when there are operators inside it. Remember that. Oh, that's okay. Remember that this is just the Hamiltonian, basically, 1 and 2 electron integrals. So normally I can't, but this is just a number, right? So I'm allowed to play this game of trace of a product. Now, and then this is just a constant, so I can pull it out outside the trace, right? So now I have e minus lambda over tau equals trace of minus 1 over tau. Trace e minus 1 over tau h effective. This is equal to 1. And so now when I see e to the minus lambda over tau, I'm going to pull it over. So let's just pull it over. E to the lambda over tau equals trace the minus 1 over tau. I'm sorry, my writing is very bad as I get further down the board. This is, let me just do something. Oops. That makes my writing a little bit better. This is minus tau to the minus 1, rather than trying to write 1 over tau, right? This will, my penmanship will look better this way, right? And unfortunately, I didn't leave myself enough space, so I'm gonna have to go up here. And this means the log of e to minus tau to minus 1 h effective of the trace equals lambda divided by tau. And so now I can write an expression for lambda is tau log trace e to minus tau minus 1 times h effective. Okay. So this gives me an expression for lambda, which is useful because I have one lambda that's showing up explicitly here. Right? And the other thing that I have is this thing right here. If I look at it, it showed up exactly here. So this trace is just 1. So I have minus tau times minus tau. Oops. So So this is my lambda term. I'm gonna pull it all the way over here. This term I'm gonna put there. It's gonna be tau times the log of the trace of E beta H effective. Oops, I'm not using beta, I'm using tau to -1. Okay, so this is my Lagrangian, okay, at a given temperature tau. Now, this is just a constant, so it's not going to affect anything, right? So now I can write in BE of tau. And I've redefined this because I've dropped the constant term that I don't care about, is minus tau. Well, it's the supremum over H of minus tau log trace E minus tau. This one, H effective minus trace of gamma. And for those of you who are more familiar with thermodynamics, you'll immediately recognize that this is just your partition function showing up, right? So this is sort of a beautiful form. It also immediately tells you this is not easy, right? Evaluating quantum mechanical partition functions is a pain in, but it's a known problem, right? So this is now a known problem. Because we regularized it, everything is nice and smooth. So while normally we would only be able to write a soup, we can actually write it as a max, right? So this now gives you the ability to write the exact functional, and it's a regularized perfect functional. Now, of course, what you really care about, BE of gamma, is the limit as tau goes to 0 from above of, right? You know, the thing you really care about doesn't happen here, right? You regularize it so it was feasible numerically, and now you have to do it, okay? But this gives you the basic structure. So can we go forward a few slides here? Just we're gonna jump. Okay, back one. Okay, so it's implementable, right? So this is the exact functional. This we call this is. You can already tell LFT, and this should be Levy-Vallon, so it should be LVT, but you know this is preliminary data, so there's typos in figures, right? But this is the Levy-Vallon. I chose this beryllium dimer stretch explicitly to show you that it's discontinuous as a function of R. It's not surprising. I mean, I knew it would show up. It wasn't surprising to me that it showed up. And it's exactly because you have a conical intersection. Right? So we had talked about that earlier with DFT, right? We talked about with kinetic energy functionals that this sort of thing would happen. I think I even had a figure for that in kinetic energy functionals. Well, the same thing shows up here. This is a consequence of the fact that when you divide your energy into pieces, this always shows up. Okay? But this should convince you that this is an implementable thing. In fact, this is done, with the full CI style calculations. So it's doable, right? Now can you go back? Next slide. Okay, so, and you just saw where this came from, right? So now I'm going to add you just tiny bits of extra information, and then we'll sort of wrap up this. So the first thing is, if you shift the Hamiltonian by a constant, right? That's a bad result, right? Because this doesn't change anything. You shift it by a constant here, you shift it by a constant here, it all cancels itself out, right? And so in practice, what we do is we add on a constraint that is just trace of H squared, okay? So that forces, this is 0 when the trace of H is 0. and it's positive otherwise, right? And that makes us choose the minimum now, or the maximum. I put this with the max. We're doing maximization. That means the maximum will occur at the point where trace of h is 0. And so I got rid of the arbitrariness of the translation. So that just is for numerical reasons, you have to do that. There's also some stuff that I won't talk about, that's some numerical shuffling. You'll notice here I already took the Hamiltonian, I evaluated this in the diagonal basis. So it's easier to do this in the diagonal, right? Next slide. Right? So here's my exactly the thing I told you we would do, right? This is the supremum, this is the constraint. And it's beautiful that the gradient of this is just the weighted average of our density matrices from all the states of the system. So this ends up being a sort of a beautiful result. Gives you have the objective function, you have its gradient, and you just go numerically optimize. I'm not saying it's easy. And there's some nasty stuff that you do in terms of how you take tau goes to 0, because as tau goes to 0, this would explode, this would go to 0, like get rid of your indeterminate form with little numerical tricks. But I mean, not important for here. And next slide. Is that next? Okay. So there's a bunch of little things that we need to talk about here. And now that we have a framework, I'm going to try to explain this theory in analogy to DFT. Right? So we're going to loop back to DFT, and we're going to talk about these questions to the extent we know, right? And we'll compare them to DFT so we understand what's going on. Next slide is perfect. Okay. So I want to think about DFT. DFT, we had something we called the right? So you had the Hornberg-Kohn theorem, right? The Hornberg-Kohn theorem says that if I give a density, there are two choices. It's the ground state for some external potential, one and only one external potential, or it's the ground state for nothing. And if it's a ground state for nothing, we say that it is non-B. So that's two possibilities. Now, the possibility for V is similar. V can go with a density it can go to something, like you could give me a potential that binds no electrons, for example, and then there's no density, no electron density at all for it. Or V could go with potentially a set of densities, right? Because you can have a degenerate ground state. So a potential can have many different densities, but every one of those densities goes with only one V, right? So subtle point, Alberto, Jose Luis, and Marco got into trouble with a referee who did not believe this, right? So this is the structure of the theorem, right? Now, we can say something very specific about the functional, only in certain cases. So the functional right? So that's the Hornberg-Kohn functional, right? Now, in general, we can't say very much about this, but when it's ensemble V representative, the supremum is a maximum. So it means if the supremum is a maximum, that means you can actually find a V that gives you the right answer. That's not always true. There's not always a V that gives you the right answer, right? So in that case, f of rho is E of V max n minus integral rho of R like this, right? And the beautiful result for this then is that I can say that df d rho of R is minus plus n, right? Just take the functional derivative of this, right? Trivial, right? Okay, so this is sort of the structure in DFT. Now, everywhere that this supremum is not a maximum, you cannot do this, right? So that's one sort of important thing to say. So here we're going to call something we call the H representability problem. The analog of Hohenberg-Kohn theorem is from Gilbert, and there's one-body operators that go with some density matrix. So if you give me a density matrix, I could find a one-body operator, but it's also possible that there's nothing, right? Now, this nothing does not happen at tau greater than 0. It's only at tau equals 0 that there could be nothing, right? But, and in the same way, a Hamiltonian could go to 1 or more than 1 if you have a degenerate state, or the Hamiltonian could go to nothing, right? And we will call these non-H. Right? Now my functional, I'm going to do it without any regularization. So I'm going to go back to the, even though it's computationally regardless, it's mathematically correct. So I'm going to go back to the one I did with Maldivi and Sidney Golden, right? So VE of gamma is supremum over Hamiltonians, E of H in minus trace H gamma, right? And just like before, right? But exactly the same argument as we normally do in DFT, right? So everything is beautiful in these. Now we have to think some about this. So how often is the soup equal to a max, for example, right? That's one of the main questions. The other main question is, you know, I wrote ensemble. Ensemble means I could take some linear combination of these densities and they're degenerate densities, and I consider that to be legit. It goes with this Hamiltonian, but it is not, there's no wave function for it. There's only a density matrix, right? Now, the same thing is true here, is it may be that there's no wave function that goes with one of these density matrices. It may be it's only some sort of average over some states, right? So I want to understand a little bit about that, right? Okay. So, okay. So what about non-V representable densities? So one thing that we can say is, and we talked about this earlier, so every V representable density is arbitrarily goes to a non-V representable density. And we said that the easy example was, you know, any density sort of has to look like this. And all I have to do is go sufficiently out to Mateo, and I'll make a very small change of a density, and I'll make the density go negative, or I'll make the density even not go negative, just go down to zero. And once it's zero, hard zero, it's not V representable. The max is a soup in that case, right? So why is the max a soup? Well, my potential, so this is rho, my V will look like this. And then in this region, I can do anything I want to. So I have a gigantic well barrier that goes up to infinity here, right? That keeps the density out of that region, right? But then after I had that thing to keep it out of the region, I know I could do that. I have no idea what I did. I can do whatever I want to over here, right? And all of them will have the same ground state density, right? As long as the ground state of this system is higher than the ground state of that system, it will never occupy it, right? So this is why it's not V representable. That means the max is not unique. There are many V's that go with that. That tells you get a supremum, but you get no maximum. You fall outside the space of potential. This potential isn't allowed in the variational procedure, right? So, so what about the non-H representable gammas? So one thing to say here is this is really unpleasant. What that means is even if I give you a place where the soup is a max and then there's a functional derivative, you're infinitely close to somewhere where there is no functional derivative, right? Which means this function is not a nice, right? Okay. Let me write this down. in an infinite basis set, every H is infinitely, or every gamma is infinitely close to being non-H representable. So let me explain why. So gamma, I will write it in its natural orbital expansion. Right? That's my natural orbital expansion for the density matrix, right? If I would plot these ends, um, um, they're going to start at 1, and then eventually they're going to get arbitrarily close to 0, right? Once they're very close to 0, I can set it equal to 0 with a very tiny perturbation, right? But if I set it equal to 0 with a very tiny perturbation, then all of a sudden, it's the same thing that happens here. I can do anything I want to H in terms of that eigenvalue, and it doesn't matter, right? So that orbital just gets deleted. It doesn't matter, right? And so it's the same sort of argument as there was before, right? So this is sort of the argument for, right? This is also a really nasty functional, right? This functional seems to be even nastier than the density functional in the sense that for density functional theory, it seems that if you give me a random density, it's usually pure state V representable. And that's nice, right? Because if I give you a density that's pure state V representable, so there's a V of R that gives me a rho, then I go to V plus delta V of R, then that will give me rho of R plus delta rho. A small change in V will give me a small change in rho. And that's only true when you correspond to a non-degenerate ground state. If it's a degenerate ground state, you make a small change in V, you break the degeneracy, and the density can change a lot, right? With the density matrix, it seems that when I give you H plus, delta H, you would have the same thing. You have a gamma, you would like to have gamma plus a small change in gamma. That would be a nice property for you to have, right? But it seems that very often this isn't true. Like, it seems that often things are not pure state. Right? There's lots and lots of mixed states, which I guess shouldn't be surprising, right? Because the space of pure state representable density matrices is much smaller than, well, the set is much smaller than the set of ensemble density matrices, right? So the structure is very similar to DFT. If you know DFT, you know density matrix functional theory. There are a few little nuances that go along the way, right? So. Okay. So questions? This is a function of their index. I sort them and focus them, plot them versus index. Yeah. Okay.
Don't be shy.
I might did not understood correctly, but so occupations of natural orbitals cannot be a hard 0?
Oh, they can be a hard 0, right? But once they're a hard 0, then in this, you have enormous freedom of what you want to do with the corresponding eigenvalue of the Hamiltonian, right? So one way of saying it is what happens. So remember, the key is we want the supremum to be equal to a maximum, okay? So let me just write a Hamiltonian that gives me a hard zero. Okay, so I wrote down my gamma. Let's write, and we're gonna just pick on one. We're gonna say I is not equal to M. And we'll say, well, I'm sorry, I just realized I'm changing notation for my natural orbitals, but okay. Okay, so this would be my density matrix with a hard zero. One of them has been set to a hard zero. Technically, it should always be the last one because I get them sorted, right? But I don't know how to use the infinity index, so I put it somewhere else, right? And if this is close enough to infinity, like if we're dealing with the neon atom and I'm looking at, you know, the 10 to the 9th eigenvalue, then this is really, really, really small, right? The asymptotic decay of that is, you know, has been worked out, right? Your Erdos number comes from that asymptotic decay. That was a paper that I wrote. But now just think about, so what does the Hamiltonian have to look like in order to get this behavior, right? Well, I don't know what it is, you know, sum of E, Q not equal to M is some but I have to prevent any occupation here. So I have to make this element that corresponds to this order has to go to plus infinity to keep the electrons out, right? But this is not a case where, this is not something you can get. This is a case where there's a supremum. It exists as some limit, but you never get there. You never get to infinity. You fall off the boundary of the set, right? Right, so this Hamiltonian has no norm, for example, right? So it's a bad Hamiltonian. And so that's what I mean by this is, as soon as you get this hard zero, this isn't a max anymore, right? If you would like to take the derivative would have an infinity somewhere, right? So that's what I mean, right?
In the, if I understood correctly, I think you mentioned in the first part that the derivation that you did is not necessarily a constructive approach. But my question is, it can be, right?
So the just
To finding functionals of the electron-electron interaction as
well, okay,
functional
I
to
guess the question is, how do you define
a way to obtain approximation.
So this way, I, just speaking for myself, have not been clever enough to make this constructive, right? So this is very much like the work that Helgacker and Andy Thiel and Andreas Savin and Francois Colonna did, directly inverting the Hohenberg-Kohn functional, right? Write it down directly, compute it directly. That, you know, Bob Morris and Parr and Barnes and Van Leuven did for the Kohn-Sham functional. It's very much in that spirit of, we can buy something, but calculating the quantum mechanical partition function is harder than full CI, right? So this is like iterative, harder than full CI to do this, right?
I think it's worth to think about it, right? To try
So, and the same, I mean, I think in DFT, people have gotten inspiration from understanding the exact structure, right? Have people directly approximated this? Well, the only sense in which it's been directly approximated is, for instance, I can build the couple cluster functional. I can do that here too. I can build you the couple cluster functional. I can build you the CI singles and doubles functional. And I will have effectively recovered exactly the same method as those quantum chemistry methods at significantly higher cost, right?
I understand what you mean, but the other question is, I mean, with these situations that you are saying of the of how easy it is to move either with the density or with the density matrix to non be representable situations. Isn't that also telling you that when you are in a self-consistent approach, let us think practical, to obtain in DFT the density or in DMFT the density matrix, that your process, your iterative process can be really tainted because, or actually wrong, because you are probably eventually, I mean, the probability that you will hit a non-B representable either density or density matrix is almost
Well,
one.
so the good news is non-B representable doesn't affect you so much, right? And it is true also that, so why does, I mean, it goes back, why does DFT work, right? So if you did root strength DFT and you just said, I'm going to just, minimize, just that, this would be terrible, right? Because your density would just be constantly bumping into the boundary where there's no derivative, right? So in practice, we never do this, right? If you do orbital free DFT, a lot of times people use the square root of the density as their variable, for example, instead of the density itself. If you do Cone-Sham, you write the density as the sum of squares of orbitals, and that gets this constraint. I get to get rid of it, right? And this was a constraint that caused me my trouble, right? And if you give me, PBE, right? That's a nice, smooth functional, right? If you give me, certainly if you give me Thomas Fermi from bicycle PBE or something like this, like that functional is differentiable as long as you want it to be. And I don't have non-B representable problems. I always have a derivative. For any density, I have a derivative, right? Now, once you do Cone-Sham, you have some weirdness, right? Because you might have a density that doesn't correspond to a Slater determinant, right? But the flip side of it, I gave you the bad part, right? Which is, oh, by the way, every density matrix is infinitely close to being bad, right? At least for the density, it's known. Also, every density is infinitely close to being good, right? So even non-V representable densities, there's a very, 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 very close V representable density. And so numerically, you can never tell the difference. There's always a derivative of it. If it's not your density, it's one that at the precision of your computer, it might as well be your density, right? So because we don't use the functional, right? That's the thing, we don't actually use the functional. Even if we did, we never take the supremum all the way, right? At some point, we're like, okay, I'm tired now. This thing isn't converging. I take my value and whatever potential it came with, and I use that. And that corresponds to a density that's very close to a density you want, and you say, it's fine. Numerically, I'm fine, right? So the same thing is going to happen here, right? Now, and as soon as you regularize, it's perfect, right? All of the problems are gone, right? That's why you regularize. It's when, Trygve Helgaker and Andy Thiel and their groups did this for DFT. They regularized first, right? Before they did the inversion, and then everything is nice and smooth. Their regularization is so strong, it's much better than my regularization in a certain sense, Their regularization is so strong that if you gave them a negative density, it would still give you a reasonable number. Right? They regularize everything, right? So they really expand it. You give them an arbitrary function that integrates the right number of electrons, and they give you a number. Right? It'll be very close. It'll be a gigantic number if it's not unrepresentable, but it's not infinite. Yeah. But I think it has to do with, I mean, that's the thing, is that all of this is, I mean, I don't know, it's the Catholic country. I'm not sure if I'm allowed to say things like in medieval times, like, there was all the, how many angels can dance on the head of a pin, right? And these sorts of things. And it's intellectual exercise, right? To some extent, this is the intellectual exercise. Like, I believe we learned something interesting, but it doesn't relate to, how does a Purie's functional work for density matrices. It may tell you, oh, be careful, there are places where this is going to be very, very hard problem, right? But the functional works,
Have
to have a
some
solid
idea,
framework is important. Right?
some idea of the
Yeah.
formality
Yeah,
below the theory that we are using. Right?
yeah, I agree. I think that's.
I think this is taking us to the question I did 2 weeks ago. But I mean, what happens if you are approaching to the exact energy from below? Something that can happen in a ESC procedure.
Yeah. So the nature of these functionals,
But they are not exact functionals.
they're not exact functionals, but let me just, I'm going to write down a functional for you, okay? That will approach each from both, okay? So, okay. So this is my functional, right? And the only thing I did is I said, well, this is a supremum. I'm going to do this numerically, right? Which means I'm going to only run so many steps. I'm going to have a maximum number of iterations that I'm willing to run, right? It can be 1,000, it can be 10,000, whatever it is, it's a certain number of iterations. Now, this functional is convex, so I can never get an answer higher than the truth, right? Which means that this is always a lower bound on the ground state, right? And in fact, the equality is probably unlikely ever to be achieved even, right? So all of these functionals in a certain sense are lower bounds, right? In any practical sense, these are all lower bound functions. Right? And this would be if you converge the SCF all the way, or the equivalent of SCF all the way. Like if you use these functionals, you'll get a lower bound, right? I'm not sure if that answers your question at all. It's okay. You can rephrase it if I did like what students do in their exams and you answer the question you want to answer instead of the question that's being asked.
Or
Can be about anything. I'm here for another. Until Jorge kicks me out of the room in 20 minutes.
no?
Okay.
Okay, we will finish. So, thank you.
Yeah, well, if there are no more
Okay.
questions, I would like to thank all
Mhm.
this wonderful course.
Thank you for having me.
We are very, very glad. There have been very exciting 2 weeks that we have had with you. We have a lot of things to do ahead, and the course was very, very good. We are very
Thank
happy
you. Yep. Thank
that
you.
you have visited.
Thank you, Professor Ayers. So it was a wonderful course. So we have a present for you from the chemical department of one
Thank you very much.
official teacher of the Department of
Okay.
Chemical Department.
Yeah, it even has a flask on it. So anyway.
Okay,
Thank you.
good. So,
Oh, no, thank you very much.
okay, so thank you again.
Thank you. It's been a lot of fun. So.